We can start. Can you hear me? Yes. Forgot to do something. I have to do the conference selfie because I do it every time now. But every time it needs to be better. So can you do, this is going to be hard. Can you do a dab like this? Can you do this? Can you all do it? 1, 2, 3. There you go. Nice, thanks. This is going to be great. All right, so this talk is about papers we love, Elixir edition. So you know papers we love. This has nothing to do with that. It's just like we just told the name because it sounded nice. But it's about papers that we used to make Elixir better, that we studied in order to implement features and to implement stuff in Elixir. So my name is Andrea. That's my handle on the internet. I'm from Italy. So most of my friends know that I am a very vocal Italian guy about food, like most Italian guys. So if you say like I want to put pineapple on pizza, I'm bound to get like at least agitated, right, or angry. So my dream in life is getting on this Twitter account, which is Italians Mad at Food. I don't know if you've ever seen this. It's like full of just such like comments from Italian guys, like so happy that there's an ocean between us guys. This is like directed to the US, right? Or obviously there is no spinach chicken pasta recipe in Italy a recipe like this is a crime worse than a murder. Anyway, we're not just offended, we're actually vomiting. It's great. A world war won't be enough to forget this. This has got to be heavy. Yeah, so like I wish I could be there one day. So I work for a company that I like to call, you know, Yelp. Yeah, but for weed. So this is called Weed Maps. So you know Yelp? Yeah, for weed. So you have like dispensaries you have maps with dispensaries and reviews of dispensaries and cannabis strains, and you can, go there. This is actually the first country, I mean, that I'm like doing this little thing, and it actually shows dispensaries because it's like you can buy it here. So it doesn't work anywhere else except for some places in the U.S. And in California, this is actually even nicer because I can say, you know, Uber Eats. Yeah, so this is the same thing in California. You can actually order online and get weed delivered to your house. And there's a really nice option that you can get like a drop-off at the corner of the street, and you can go in the car and buy weed from the guy in the car, like a proper like drug deal. I mean, it's for real. You can choose drop-off. Yeah, it's real. Yeah, it's amazing. So I assume you want to work there, and this is the link. Do we provide free weed? No. This is a question that I get a lot. We do not provide free weeds, but in the office there are rooms for smoking, and like it's encouraged, I would say. So I don't work at the office. Just to make things clear. Yeah, I work from home. What? Yeah, we should. Yeah. All right. So. Talks about Elixir. So if you don't know, Elixir is a functional programming language with a focus on concurrency and fault tolerance. It runs on the Erlang virtual machine. So Erlang is this kind of older language made for telecom systems that has all these nice properties that we want. And Elixir is relatively young. It's, I think, 5 years old or 6 years old. And the Elixir core team is now 6 people. That's me, so I'm in the team as well. And the core team is definitely not people that I would call from academia, so it's mostly industry people. So there's a few like master's degrees and bachelor's degrees, but there's no PhD, for example. No one is doing their PhD. So it's people that are actually working on stuff in the industry world. Nonetheless, we really love the research, and we really love to study research and dig in order to find solutions to the problem that we have. And in this talk, I want to talk specifically about 3 cases where we use a lot of existing research in order to implement features in Elixir. And those 3 cases are formatting code with a code formatter that's now in Elixir, diffing data structures for test failures we're going to see, and property-based testing. So all these three things are in Elixir right now, and they're all stem from research and papers that we read and implemented in the language. So the first one, formatting code. So we really wanted, a few months ago, we really wanted a code formatter in Elixir. We wanted a code formatter because it's really nice for newcomers because they just run mix format. There's a command and it just formats your whole code base in a consistent style, and they don't have to care about how do I indent this or how do I style this. It's consistent. It allows you to have consistency across teams, organizations, and throughout the whole community. And it eliminates style discussions because it's just everything is decided by the formatters. The code, the style is enforced. So we really wanted this in the language. And this is not really hard to implement until you decide that you have to have a line length limit as well in the formatter. So if you don't have a line length limit, you just print your code. You just have an AST and you just print your code. And then whenever there's like a do end block, you just go on a new line. And that's it. But this way you are bound to get like huge lines. For example, lists with a lot of elements in the source code would go really long lines. So what the hard part of having a code formatter boils down to is printing code with a line length limit. So printing code that fits in a line length limit. So what am I talking about? Say you have this code. This is a map in Elixir. You have a foo key, and then a list of integers, and you have a bar key, and then a buzz string. So you have a line length limit of 30. Okay, then the formatter can just print this out on one line, and it works. And it's like you can just print it out like it is. What if we bring down the line length limit to something like 25? Now the thing doesn't fit in one line anymore, right? So the formatter should be able to actually go ahead and split this at the right point so that it fits, and in the minimal amount of splits so that it fits on one line. So in this case, the formatter would have to do something like this, where it only splits the key value pairs. So it puts the map brackets on their own lines, and then it puts one key value pair on each line. So this works with the line length limit of 25. It's like the smallest break you can do in order to fit it. But what if we actually make the line length limit even smaller? Then we still have a problem, and then the formatter needs to do the same thing. And in this case, it should split the list. So it should always split where it makes sense, and it should do the minimal number of breaks, right? Line breaks. And this turns out it's not the easiest problem. It's quite a hard problem, or not. Yeah, it's quite a hard problem. So when we were implementing this, we started looking into this. We started with a paper called "The Design of a Pretty Printing Library" from John Hu. So this describes how. So this paper kind of introduces the idea of algebra documents, of an algebra of documents, and in fact, this translates to the inspect.algebra module in Elixir that implements this stuff. And this algebra of documents describes a bunch of documents that can react differently to how you split them. So there's a text document that's the simplest document, which is just text, and you can't break text. For example, if it's a variable name, you can break it in the middle. Then there's a concat document, which takes two documents and concatenates them. And then for example, there's a nest document, which takes a document and nests by a given amount of columns when it breaks. So you can do stuff like indent stuff that you're printing. And then there's another important one is the line document, which forces a line break between two. It concatenates two documents, forcing a line break. So if we have these documents, we can do something like represent the list on one line by using concat, right? So we use, this is missing spaces, but it's not important, but we use concat to concatenate all the parts that form the list, and they will all end up on one line, right? If we want to print it on multiple lines, we can use the line document and the nest document. So we create a document that contains the bracket and then 1, 2, 3. Since 1, 2, 3 are broken up from the original bracket, if we nest them, they go up they go 2 spaces on the right, and then we can just add the remaining bracket. So this way, we print it with the algebra. We print it on multiple lines. The problem with this now becomes, how do you decide whether to break or to put everything on a single line, right? How do you decide whether you should what you should do when you encounter something like this. And then there's another paper that we use for this, which is called the Prettier Printer from Philip Wadler. And this paper introduces the idea of groups. So basically, if I take something and I put it in a group, then when I'm rendering it, I can treat the group as something that can either be broken up or that it can be rendered on a single line. And in this case, we can basically decide that concat will behave that it will concatenate strings when they fit, or it can be a breaking point where we can break in case the things don't fit, right? So in this case, this is exactly what we need, because if it fits, if everything fits, we should put it on a line, and the nest won't have any effect, because it's like it only has effect when you break in multiple lines. So we just put it on a single line, but if it doesn't fit, concat basically turns into line, and we break 1, 2, 3, and we nest them by 2, and then we put the parents on another line. So basically what the code ends up doing is choosing between the document or the document with the concats replaced by line breaks. So when it's choosing, if the document fits without line breaks, so it renders on a single line and it fits the limit, then we use that. If it doesn't fit, we replace the concat with line breaks and we print it out. So the problem with this is that we have a strict language. So whenever we want to do this, so a strict language means we have to evaluate the arguments to the function before evaluating the choose function. So the problem with this becomes that we have to, so it grows exponential, because we have to render the doc for each group, when we're choosing, we have to render the group without line breaks, and then we have to render the group with line breaks, and this kind of propagates through the whole tree, and it means like a lot of rendering and very, very slow for doing something that should be lazy, right? And it should be lazy because the original papers that I mentioned, they were for Haskell, which is a lazy language, so they didn't encounter this problem. They worked. Turns out someone called Christian Lindig did research on this, and he published a paper called Strictly Pretty, and this is exactly the implementations that we use, described in the Prettier Printer and in the other paper, but for an eager language. In this case, it was OCaml, so we just took this and ported the implementation straight up in Elixir, and it's exactly what we want. And then we added some documents as well. So for example, we extended the algebra of documents that the papers introduced, and we added something like color, which is used for, so we use this stuff also when printing terms in the interactive shell. So color is used to just do syntax highlighting, and it doesn't do anything about nesting or breaking. Then we introduced cursor when nesting, which is something that we use for the code formatter, which nests where the cursor is, so we can indent stuff in an easier way. And we added a bunch of more, but the idea is that we were really glad that these papers introduced a very simple algebra that we could extend on for our needs, because our needs were a bit different than the ones highlighted in the paper. And the paper, of course, tries to find a general solution, a very general solution to a problem, and we had to kind of go and add real world stuff for our specific use case. So this is related to code formatting. Then something we did that stemmed from research as well is diffing of data structures. So we use this in tests. So say you have this is a test failure from XUnit, and it's testing something that's definitely going to fail. So it's asserting that the string hello world with a question mark is equal to the string hello, comma, my world, which is a bit different. And this is going to fail, of course. And having failures like this, what we wanted is how can we make it clearer how the things that we're comparing are different, right? So in this case, it's pretty straightforward because they're very small strings. But in some cases, you have huge strings that differ by only a few characters here and there. And in those cases, it would be really, really nice to have a diff. So something like this, a diff that tells you, like a git diff, right? That tells you where the differences between the strings are located. So in this case, it's just standard diff. So it says, so H in red means like the H isn't in the second string. The H in green means that is in the second string. You know how diffs work. So when we wanted to do this, we started looking into research on how to do diffing between sequences, basically. And we found this paper called an OND difference algorithm and its variations by Eugene Myers. And this paper, the whole point of this paper is to find the shortest edit script to turn a sequence A into a sequence B. So a sequence A and a sequence B in our case can be lists or string. And the edit script is basically a list of commands in order to bring sequence A into sequence B. So there are 3 commands. The first one is, we call it EQ, but it's basically leave this part alone. Then the second one is delete something, and the third one is add something. So through these 3 commands, you bring the sequence A by adding stuff or removing stuff or leaving stuff untouched, you bring it into sequence B. You transform it into sequence B. And the whole point of the paper is that it reduces this whole thing to finding the shortest path in a graph, and then it does a bunch of stuff with that. The paper is tailored for, or at least the algorithm is tailored a little bit towards diffs that are small, so things that are pretty similar, but have some differences. So the OND time complexity, where the D is a parameter that is related to how similar the 2 sequences are. So this is very good with stuff that has like not a lot of changes. And source code is a great example, right? When you're changing source code, the changes are not huge. They're usually a small part of the whole sequence of the whole text. The paper mentions the DNA strand mutations as well, or you want to just find some differences between the 2 mutations. So it's really good in those cases. In our implementation looks something like this. So you have this Myers difference function. It's in list and it's in string as well. So just in the collections that we care about. And you see if we're doing the difference between the list 1, 4, 2, 3 and 1, 2, 3, 4, this is the edit script that we get, right? So we say leave 1 alone, then delete the 4, then add 2 and 3, leave 2 and 3 alone, and then add the 4 at the end. And this is going to turn the first list into the second list. And basically, once we have this, so we use the paper to implement this algorithm. Once we have this algorithm, it's just a matter of colorizing, basically, the diff when we're doing, when we're reporting tests. So we just say, yeah, colorize the deletions as red and the additions as green, and then leave everything else alone. And this is just how it looks. We didn't do any modifications to the paper this time, because it was just like straight up what we needed, which is great, because we didn't have to come up with anything. And we also used another paper for enhancement to this, which is a paper called String Matching with Metric Trees using an approximate distance. So this paper introduces a back distance between strings. And right now we're using this so that since the algorithm is optimized, so the algorithm that we described in the Myers paper is optimized for strings that are pretty similar, where the diff is not big. We use this algorithm, the back distance algorithm, which is a very fast way to calculate in a very approximate way how different 2 strings are. And we use this so that we only compare strings that are kind of similar, that we know are could be similar. We don't compare strings that are completely they're very, very different, because the diff in those cases usually it's not really helpful, right? Because it would just be a big red thing and a big green thing. Yeah, so we use this back distance thing just to kind of test the water and see if we want to use the actual more time-consuming algorithm or just not emit the diff and not print the diff. Yeah, so this is research we used for diffing stuff. In XUnit, on the outside it's a very small feature, because you just it's just diffing on tests. It's a really nice feature, but the work that went behind it is a lot of work. And the last thing I want to talk about, the last of the 3 cases I want to dive into, is property-based testing. So property-based testing is a testing technique which consists basically into taking, so you have a piece of code you want to test. You take a piece of the shape of the input that the code can take. So for example, if your code is a sorting function, then the shape of the input is all the lists, right? A function that sorts lists, then the shape of the input is all the lists. So you take this, you define the shape of the input of your code, you define properties of the output of your code that are true regardless of the input to your code. So if I have a sorting function that sorts lists, the shape of the input is lists, and the properties of the output can be, for example, that the result is a list, which is true for every list I feed to the sort function. We know that the list has the same number of elements. The sorted list has the same number of elements as the non-sorted list. So we know some properties of our code that are true regardless of the input. And then you take a property-based testing framework, which introduces randomness and just generates a lot of inputs and feeds them following the shape that you described, and feeds them to your code, and it asserts the properties of the output. So it generates random stuff, feeds it to your code, and then asserts that it's true. Then generates new random stuff, and you can usually configure how much this is done, but it's done a lot. That's the idea. And the idea behind this is that it will both test your code with many more inputs than you would do with something like unit tests, because it generates inputs at random that you usually can predict what inputs you would get. And it also kind of shifts the way you think about your code, because it forces you to think about the properties that your code has. It forces you to think about what kind of inputs your code can take, what is always true. So it's kind of a mindset plus testing technique thing. So this is an example. This is using an Elixir library, but it's not important. But this is what I was talking about, sorting lists. So we just say the shape of the input is list of term, so any list of any term. And we say basically check that all lists out of, like this is in math, it would be for any list in this set of all the lists of terms. Then we sort the list, and we assert that the sorted list is a list, and then the length is the same. So this is just a working property-based test for the sort function. So it's not listing all the properties of the sort function, it's just listing a few, but this is a proper test. And so I got really interested in property-based testing for a specific reason, because we were having problems with how we were working on two functions on the Elixir, or we were working on bugs on two functions on the Elixir core, which were string.starts with and ends with. So functions that check that a string starts or ends with another string. And these functions, we were having trouble deciding what to do with the empty string. So do all strings start with the empty string, or no string starts with the empty string? What about the empty string? Does it start with the empty string? All this kind of stuff. And we didn't know how to, like, what is the right way of implementing this, right? What's the right behavior? And we reverted to property-based testing, which basically says, just put this into a property, like what's the property that is true for all strings, right? For these functions, for all strings, what's the property that holds? And we... What was term again in the previous slide? Term? The function term? Term is just, so a list of term is just like a list of any term. It's just like a list of any possible data type in Elixir. So it will generate just random lists with integers or tuples or other lists or like whatever in them. It's just lists of any term. And this is like if you have, I'm using like a made-up sort function, but whatever, like if you use enum sort, for example, from the Elixir library, this property is true, right? Because like the sorted thing is a list, and then the length is the same. Like whatever you sorted, the length should stay the same, right? The actual elements should stay the same, yeah. So regarding string, the property that we found out we wanted our string starts with and ends with implementations to have is this. So for any string S1 and S2, the concatenation of S1 and S2 should start with S1 and end with S2. So this is very reasonable, right? If you put it like this, it makes a lot of sense, right? So if I concatenate two strings, of course, it starts with the string on the left and ends with the string on the right, right? And it turns out I wanted personally to run this through property-based testing. Problem is that property-based testing in Elixir, there were only Erlang tools available, and it didn't scale very well because the Erlang tools all have different license, so we can't use them for the Elixir code base. So this all led into the rabbit hole of, like, would it be that hard to write a property-based testing library? I mean, yes, it's like, yeah, it was a bit hard, but it was not terrible. And the result of this is that now we have a property-based testing library for Elixir. So when I started writing this, the first paper I had to read is the original QuickCheck paper. So this paper, QuickCheck, lightweight tool for random testing of Haskell programs, is a paper from Klassen and Hugh about a library called QuickCheck for Haskell. And this paper introduces all the ideas that I mentioned about property-based testing. So describing the shape of the input, generating random data, and asserting properties of the output. These are all described in here. So all the base ideas are in here. But this paper, I mean, the QuickCheck library relies heavily on types. So it makes sense because Haskell is a statically typed language. So you have so for example, if you have a type called color, which is red, blue, or green, then you would, so this QuickCheck library introduces the arbitrary class where you just define an arbitrary function and for the type, and then you describe how a type generates its random terms out of the type, right? So it's like you rely heavily on the type in order to generate stuff and to know how to generate stuff. So this didn't work for Elixir because Elixir is not statically typed. So we had I started looking at other implementations, and I didn't find anything in the existing research or papers, but I found the closures test.check library, which is exactly the same idea. So it's QuickCheck, but for Clojure. And for Clojure, it's nice because we have a lot in common with the language. So all the data structures, like many data structures, work the same. It's functional like Elixir, so and it's not statically typed, right? So we had the same problem solved. And this implementation is what actually led to our implementation, which is called stream data. And stream data, so this syntax is from stream data, which is our, this pure Elixir implementation. So this is just a test that, this is a test that property we wanted to assert, just written in Elixir stream data syntax, just asserts it as for any string S1 and S2. The concatenation starts with S1 and ends with S2. And it turns out, if you're curious, that the empty string is always true for everything, right? Because like if the S1 is an empty string, then this should still be true. So this starts with and end with should always return true if the left or right side are the empty string. And when both of them are the empty string, it should return true as well. So it was just like very easy to decide this once we encoded this property, and we ran the tests, and yeah, the empty string should always return true. So the difference, so there's some, like I mentioned, the QuickCheck paper is very type heavy, or it relies heavily on type. Our implementation does not. So our implementation is mostly focused around generators, and generators are what generate data, and that's kind of the most important part of property-based testing. And for us, generators are just functions that take an input, which is a random state, just so that we can replay the same sequences of generated data if we want, to make tests reproducible. And these functions take a random state and return a lazy tree. So the lazy tree is the whole abstraction that powers both Clojure test-check and Elixir's stream data. And the lazy tree is substantially just a value plus a recipe for shrinking it. So I didn't mention what shrinking is, but property-based testing, it usually, so the idea is that you generate random data and then you feed it to your code, and if a failure is found, usually the data is complex, right, or it's very noisy because it was generated at random. So it could be that something in the data that we generated caused a failure, but it can be really hard to spot it because the data is very, very noisy. So the idea with shrinking is that, again, I want to bring that noisy data into a smaller, simpler version of that data that still causes the failure. So it's about reducing complex and noisy data to simple data that still causes a failure. So this is a really important part of property-based testing because, again, when I run a property-based test, it will say, okay, this failed, and the minimal reproducing or input that I found is this. And the idea with lazy trees is exactly this, to bundle the way of shrinking, the generated data with the data that we generate. So when you call something like stream data.integer and you take an integer out of this generator, what you actually get is something like this. So the root is the value that we use when doing property-based, when running your code and testing your code. And as long as everything goes fine, we don't use the rest of the tree. When there's an error, we actually go down the tree and try the values down the tree. So in this case, in order to find if the same error applies for simpler values. So for integers, simpler values mean closer to 0. That's our measurement. And this tree, you can see, is just like 3, and then you have 0, and then 2, and then 2 as a subtree of 0, and then 1, and then you have 0s again. And the whole idea is that they're called lazy trees. So this would be really complex to generate all of these just to get the tree most of the time, most of the time, right? And just ditch everything else. So that's why they're called lazy trees. It's because the rest of the tree is not calculated unless we actually go down the tree. So when we generate stuff, we generate the root, which is a concrete term, like 3 here, plus we generate a function that will, it's a stream in Elixir, but it's just essentially a function that when you actually need to go down the tree, you can evaluate and it will give you terms. So the algorithm looks basically does, it checks 3. If 3 works, then it generates another term and it never evaluates the rest of the tree. If the 3 fails, then it will try 0. Does 0 fail? If yes, that's the most minimal term that fails. Otherwise, it will try 2. And if 2 doesn't fail, and so on and so on, it will go down the tree and explore the tree in order to find the smallest failure possible. And the really, really nice thing about lazy trees that made the implementation of stream data quite simple, I think, is that they're really easy to compose. So the way we compose generators now is just about composing trees. So if a good example, I think, is what if we want to map a function over a generator, right? So we want to map a function so that every term that the generator generates is run through that function before being returned. So in this case, we're turning the stream data integer generator into a generator of even integers, so we're just multiplying by 2. And the way map works is it will just map the function through the whole tree. So it will do it eagerly on the root, so it will actually do it on the root, and it will register the computation on the other terms on the rest of the tree. So the idea is that when I map the function times 2 over the integer, then the values that it generates the tree has the function mapped over it as well. So it would just look something like this, and now it's a tree that it's a value that actually shrinks properly according to the generator, right? Because the problem would be that if I take this value 6 out of context and I shrink it as an integer, it could shrink to 5 or 3 or 1 because it's just an integer, right? This way, we're actually bundling the way it should shrink with the value. So it shrinks properly, and it shrinks only to even values. So this is a really, really good abstraction, and it makes composing of generators really, really easy. So this was property-based testing, again, coming from the research side of things. And then we have some honorable mentions of other papers that we used that were very important to the development of Elixir, but that I won't dig into. The first one is this one called How to Make ad hoc polymorphism less ad hoc. This paper we used for the inspiration on how protocols work together with the closure implementation of protocols. Then this is a very old paper called Recursive Functions of Symbolic Expressions and Their Computation by Machine. This is the LISP paper, and we basically, this describes M expressions, and Elixir is a bunch of M expressions, so this is definitely, it was definitely used when working on Elixir. Another one that we use is Advances in Record Linkage Methodology, and all the rest of the title, and this is from a guy called Matthew Jarrow, and we use this for distance between strings. So I mentioned the back distance before, that we only use that in diffing, but yeah, we actually have a function called string.GarrowDistance that actually measures in a more precise way the distance between two strings as a float between 0 and 1, and it was taken by, the algorithm is from this paper. And then the last one is from an issue of Monad Reader. I'm not sure if it's classifiable as a paper, but it's called Iterative Teaching Null-Fold New Tricks. And this was used to get ideas on how to implement enumerables in Elixir, so how to have a general way of iterating over collections and reducing over collections that doesn't depend on the collection. So the collection only needs to implement the way to reduce over itself, and then you don't need to do anything else on the specific collection, and you have a whole library of functions that you can use to work with collections. So the conclusions, the existing research is really, really great. You'd be surprised how many things have been solved by other people. So definitely our recommendation is to look at the research and look at what was published when you're trying to solve a problem, because usually there's algorithm or ideas or anything relying around in papers. And another nice thing that we really like about this is that the research from the industry side, I mean, this is what you perceive, that research, it really strives to solve problems in a general way or in a very simple way or in an elegant way. So this is like an example is the algebra documents paper, right? So it tries to find a very minimal algebra of documents that you can use in order to, and then you can extend that, and that's exactly what we did. So you start with a very small set of core ideas and then just build up on that. And the last thing I want to mention is that we particularly love John Hughes' papers. So this is like a talk by Jose, which is the creator of Elixir, if you want to go watch it. A talk he did at Lambda Days called HCD, which is U-driven development, just because stream data, so the property-based testing stuff and the code formatting stuff were very influenced by his work. So we're definitely thankful. And that's it. Yeah, that's all I have. I think we have time for questions, right? Yeah.
Thank you for an amazing talk. I just wanted to mention that there is a really nice paper for edit distances which uses block moves. Mm-hmm. So instead of saying 2 was removed, 3 was removed, then equal, 2 was added, 3 was added, you could say 2 and 3 were moved to the end.
Okay.
So if you're interested, I have the name of the paper.
Yeah, just send it to me.
Okay.
Follow me on Twitter first, so I get a follow.
Okay, will do. Cheers.
Just kidding, you just tweeted.
So given that there's so many academic papers, how do you find the ones you need?
Google, I guess. You just or references at the bottom of other papers. That's a good way. That's why they're there, I think. And I don't know. This way, like someone mentions, oh, there's a paper that does this. It's That's pretty much, I think. Any other questions? No? All right. Thanks.
Thank the speaker.